Hello, I would like to show one often overlooked way to understand elastic and inelastic collisions regarding conservation of momentum in a one-dimensional framework, and that is to consider the center of mass of a system. Okay? Imagine that we have two balls, both of which are exactly 1 kilogram. The way this is shown on this fet.colorado.edu, click on physics, click on motion, click on collision lab. When you show this simulation, the size of the ball is meant to be something related to the mass of the ball. In other words, let's assume constant density, 1 and 2 red and green balls. Okay, so let's assume it's an entirely elastic collision. If I was to show the center of mass, the center of mass, notice the center of mass is exactly halfway between the two balls. In fact, hopefully you can see if I move ball 1 to the left, the center of mass moves to the left. If I move ball 1 to the right, the center of mass moves to the right. But it's always going to be exactly halfway between the two balls when they're both the exact same mass. Okay? So notice that's what's going to be the center of mass. Now, in a previous video with elastic collisions, I showed that the center of mass, I showed that when two balls have the same mass and they hit each other elastically, one ball should stop, the other one should start going if one is at rest. And in fact, all the kinetic energy and all the momentum should transfer into the second ball. Okay? So let's go ahead and examine that, but let's keep our eye on the center of mass. Notice the center of mass keeps moving as if it was unimpeded in this simulation. Let me show it again. The center of mass, even if the center of mass is far to the left, the center of mass will always be halfway between the objects, and that continues to move as if it were unimpeded. Okay? Let's see if it's a little bit different, such that it's an inelastic collision. Now, it's perfectly inelastic. The objects are going to stick together. Notice that the center of mass is going to move such that it's still going to be halfway between the objects. But notice that at first it's moving somewhat fast, and then it just, again, continues to move sort of unimpeded. Okay? But it just stays at the interface between the two objects which are the same mass. Let's do a silly, more interesting example. Let's make the center of mass a little, let's make ball 1 to be twice as massive as ball 2. Where do you think the center of mass should be? Still halfway between them? Should it be closer to ball 2, closer to ball 1? And what fraction? Pause the video if you need to. And welcome back. I think it should be 2/3 of the way towards ball 1. Why? Because the two balls have 3 kilograms total mass, and then this has a mass of 2 kilograms. So if this is 1 meter, then this ends up being 1/3 of a meter. This ends up being 2/3 of a meter. You could think about the center of mass almost like a weighted average, the weighted average location of the mass. So let's go ahead and perform the elastic collision experiment again. And notice the center of mass is closer to ball 1 than 2, and again, just continues to move as if it were unimpeded. Okay, watch it one more time. Keep your eye on the little X. Okay, it's moving along at a constant velocity and continues to move along at a constant velocity. Even after the collision, the idea is that the center of mass keeps moving at a constant velocity. Let's see if we can look at how this is different if it's an inelastic collision. So, with an inelastic collision, the first half is absolutely no different, and then the center of mass now moves along, and it's closer to ball 1 than 2, but again, there's sort of this unimpeded part to it. Okay? But notice, though, the center of mass isn't moving as fast as it was. Okay? So, notice that the center of mass was moving at 1 meter per second before, but now the center of mass is moving at 2/3, okay, of a meter per second. So in an inelastic collision, because kinetic energy is lost, the center of mass does continue to keep moving. It's just that it is closer to the larger mass than the smaller mass. Okay, what if we have two objects that are going to hit elastically, but they have the same momentum magnitude but opposite direction? What if red is 2 kilograms and 1 meter per second for the velocity, and then green is 1 kilogram and 2 meters per second for its initial velocity? Okay, so let's see if we can get that. The center of mass is a little closer to 1 than 2. Let's see what happens. Notice the center of mass never moves. And that's because, notice that the center of mass is closer to 1 than 2. 1 is going to approach this point slower than 2. 2 is going to approach this point faster than 1. But the center of mass won't move because the center of mass will be the collision point. And furthermore, after they collide at the center of mass, they continue to more or less move their separate ways. And by the way, when I say that it's the collision point, I should say that at the moment they collide, the center of mass is closer to mass 1 than mass 2, as it was in the inelastic collision. But at the moment they collide, again, the center of mass still does not move. Now you can imagine something more complicated, where the objects are moving in opposite directions, but they're moving at the same velocity, but this has twice the mass that this does. So notice the center of mass will move, and again, the center of mass continues moving unimpeded if it's an elastic collision, because there's no kinetic energy loss. But if this were to be an inelastic collision, notice the center of mass would then start moving to the right, but it would be slower. Okay? So notice, center of mass is one interesting way to sort of study conservation of momentum. This is not something we focus much on in the calculus-based Physics 1 class that I am teaching right now. But notice that one way to define the momentum of a system is to define the center of mass of many objects. And the total force is the change in momentum over time of that entire collection. Basically, you could think of it as if it were all on the center of mass. Okay, thank you very much for your attention. And please smash that like button, give it a thumbs up if you enjoyed this video. Subscribe to the channel, and I will see you in the next video.